Welcome to Future Talk. On today's program, we're going to talk about quantum computing. It's a method of computing that's still in its infancy, but it's very different from conventional computing. Instead of using bits, which can only have a value of 1 or 0, quantum computers are based on qubits, which utilize principles of quantum mechanics and can be in several different states at the same time. This enables it to solve certain types of problems much more efficiently than conventional computers. My guest is a leader in quantum computing. He is Matt Johnson, co-founder and CEO of QCware, a company that develops algorithms and software for quantum computers. Matt is a member of the governing board of the Quantum Economic Development Consortium. He started his career as an Air Force officer. He has an MBA from the Wharton School, and he's also an avid swimmer who once swam solo across the English Channel. Matt, welcome to the program.
It's good to be here, Marty. Thanks a lot for having me.
So what exactly is quantum computing?
I think in your summary you put it fairly well. So the fairly inscrutable technical definition is what I'll give first, and then let's go through what that means in plain English. So quantum computing is a new computing technology that exploits principles of quantum mechanics in order to calculate solutions to certain problems more efficiently than you could do with a classical or conventional computer.
Now, I understand that quantum computing uses something called qubits instead of the ordinary bits we're familiar with. What exactly is a qubit?
A qubit is the fundamental building block of a quantum processor, a quantum processing unit, and it's equivalent to a transistor, roughly equivalent to a transistor, which in turn is the fundamental building block for a classical processor.
Now, what kind of problems would a quantum computer be better at?
So, in principle, the reason quantum computers were first conceived of is as a tool to model what happens in quantum systems. So what happens with electron interactions or chemical reactions. So natively, quantum computers are really designed to efficiently solve those sorts of problems. But as more algorithms are developed, more quantum algorithms have been developed, the types of real-world problems that can be addressed by these machines have expanded. So in addition to quantum simulation, which is really the bedrock use case, or the type of problem that these machines can solve, there are also algorithms built that allow it to solve optimization problems. There are types of machine learning problems like classification and recommendation, for which there have been quantum algorithms built. There's also, of course, another canonical quantum algorithm called Shor's algorithm, which is able to do things for cryptology. It can break RSA encryption.
Now we have a number of images which explain some of the things we're talking about. Can we see that first image, please? Okay, so what are we looking at here?
We're looking at the physical system that encloses a quantum processor. So this is colloquially referred to as a chandelier, and this cluster of wires is the basic system that is controlling the quantum processor. Now there is, in fact, this machine is not operating right now, but it would be cladded, and there would be a dilution refrigeration system that would kick into gear, which would cool the quantum processing unit to near absolute zero. So this is a particular design for a particular type of quantum computer.
Now, why does it require so much more cooling than a conventional computer?
So let's back up just a second and talk about the hardware architectures or the technology approaches for quantum computers, and then we can get back to that answer. So in fact, there are various technology approaches, various quantum computing architectures. This particular one is probably the easiest to construct, and it uses superconducting qubits. So it's using effectively loops of wire which have superconducting properties. When those wires, or these qubits, are cooled to near absolute zero, they can exhibit these quantum mechanical properties, which in turn allow these processors to work more efficiently, again, for these certain problems than classical computers. But in addition, if we do talk for a second about the other technology approaches, in addition to superconducting qubits based processors, there are also processors based on ion traps, or that use ion traps as the processing protocol. There are also ones that use something called topological qubits, and there are ones that rely on photonics, or in this case using photons as a qubit.
So there are competing technologies to see which one is going to design the most successful qubits.
Correct, or the most successful, the most powerful processor. In fact, the types of quantum computers that have proven to be the easiest to build right now are the ones based on superconducting qubits. These are actually devices that are macroscopic. So a qubit, this physical device for superconducting qubits, is less than, the loops of wire are less than a millimeter in diameter, but they're still relatively macroscopic. For these other technology approaches that I described, the qubit in those cases is not something like a loop of wires, but it could be an atom, it could be an ion, which of course is an atom with one too many or one too few electrons. It could be a photon, or it could be a number of other physical matter systems. The point, though, of each of these types of qubits is that they can use quantum mechanical phenomena, or they display that these phenomena that you've heard of called superposition or entanglement, the very things that allow these qubits working independently or as they interact with other qubits to allow you to calculate solutions to certain problems with fewer steps. And that's where you get the efficiency gains from a quantum computer, in that there are fewer operations required to solve particular sorts of complex problems.
Okay. Let's take a look at the next picture here. Can we see that next one, please? Okay, what are we looking at here?
As the label on this processor shows, this is a quantum processing unit produced by Google, and the name of this processor is Bristlecone. Google announced that it is fabricating a 72-qubit processor, and this happens to be a photo of that processor. And Google has announced that they will be attempting to show what they refer to as quantum supremacy using that Bristlecone processor. And what that means, and I don't want to put words into Google's mouth, but Google is going to run a particular mathematical problem on that processor, and the objective is to prove that that particular problem can be solved more efficiently on that Bristlecone processor than on any arbitrarily powerful classical computing system.
Now, a classical computing system, on one chip you have literally billions of transistors, each one representing 1 bit. Now you say this has, what, 72 qubits, doesn't sound like very many. Is the goal here to keep shrinking the qubits and fitting more of them on the same surface?
In this particular case, I don't, again, want to put words into the mouths of the quantum engineers who are designing this, but the goal wouldn't necessarily be to shrink the physical size of the superconducting qubits that are the basis of that particular processor, but certainly to put more processors onto a single quantum processing unit. If you, again, talk about trying to reduce physical size of the physical dimensions of a qubit, as I mentioned, there are other types of qubits which are obviously at atomic scale, so they would be smaller. But yeah, I hope that answers your question.
Yeah. Is that technology developing? Is it the long-term hope that qubits will be as small as transistors, and you'll be able to get billions of them operating at the atomic level using real quantum mechanics instead of simulating quantum logic?
Well, actually, the primary goal isn't necessarily to grow from 72 qubits to 1 billion qubits. The The most important problem that all of the groups that are building quantum computers are trying to do is to build better quality qubits. And that's really, in layman's terms, I guess, the objective is to have qubits that have lower error rates. So in classical computing, we would talk about a transistor or a gate having an inadvertent bit flip. That would trigger an error in a calculation on a classical processor. There's an equivalent phenomenon that can happen in quantum processing, and that's when a qubit that is not of very high quality or very high fidelity can also collapse into a state, and that would cause your calculation to collapse and return an incorrect solution to the problem.
So this hardware is not quite stable yet. There's a lot of work to be done before it's stable enough to rely on, sounds like.
Yes, the hardware has certainly emerged from the experimental stage, and the hardware development has found its way into the engineering groups of all of these large technology giants that are building these machines, as well as to well-funded startups. And so if we did think about the hardware landscape, there are at last count 24 commercial companies that are funded and that are building quantum computing systems. And that ranges from the large heavyweights like Google, IBM, Intel, Microsoft, to fairly powerful startups that are also competing like Rigetti, IonQ, PsiQuantum, and a list of others.
We have a few more images to show. Can we see the next image, please? Okay, what are we looking at here?
You're looking at this, in this case, this is the system for IBM's currently 20-qubit processor. This would be the fully clad and very nicely presented IBM superconducting machine. So again, you're looking at a large physical system, but in fact, the business end of that whole large system is a quantum processing unit that can fit on the palm of my hand just like a CPU can. So all of that system around it represents the environmental controls you need: vibration dampening, RF shielding, cryogenic cooling. All of that is doing that in support of, again, this particular quantum processing technology, this superconducting qubit-based system.
Okay, and I think we have another picture. Can we see the next picture, please? Okay, and what is this?
So this is, as it appears, this is a machine built by D-Wave Systems, which is a Canadian company. The peculiarity of D-Wave Systems is that of those 24 hardware vendors that I talked about, 23 of them are building circuit or gate model quantum machines. Those are roughly equivalent to the kind of gate-based quantum or processing that you have classical machines. With D-Wave, they were really the pioneer in quantum computing, and they're using a different protocol to calculate solutions to problems. They're not relying on a circuit model architecture, but rather something called quantum annealing. And their machines are really tuned to solve a particular type of problem, optimization problems, binary or discrete optimization problems, and derivatives or variants of that. But what you are seeing is this large boxy unit is really just the cladding that in turn is surrounding all of the cryogenic and other environmental systems.
So what would be an example of the kind of problem that this could solve a lot better than a conventional computer, a practical, real-world type of problem?
Okay, so just to baseline kind of ground truths, for all of the machines that you've put up on your screen and for everything out there, none of the quantum computers that have been built so far can solve real-world problems more efficiently or better than existing classical computing hardware. So that intercept where quantum computing will outperform classical computing has not yet been achieved. But if you look at where there's evidence for outperformance, once the hardware is more mature, and that should happen in the near future, that intercept is coming closer, the categories of problems that a company like ours focuses on is, again, quantum simulation, which is useful for designing chemicals and materials and understanding chemical reactions. That's certainly, probably, in our view, going to be the first area where you'll see outperformance or some wow factor in using quantum processors. That hasn't been achieved yet, but it should. Another area where there's relatively high confidence is using quantum processors to calculate optimization problems. And those could range from transport and logistics problems, where you're looking at, let's say, airspace and trying to manage optimizing flight paths of various air vehicles. It could also be used in quantitative finance. So when you think about large banks or hedge funds that are solving optimization problems important for things like risk management, it can be used there. And there's a wide range of other optimization problems in manufacturing and retail where quantum processing can be useful. A third area that has certainly gained a lot of attention, but for which there's less quantum algorithmic development to support the thesis that it'll be useful, is machine learning and artificial intelligence. As I mentioned, there are quantum algorithms that have been developed that can perform machine learning tasks like classification and recommendation and training, algorithm training. But yet, when you study the mathematics that underpin those algorithms, there's very limited evidence that they can beat currently the best-in-class classical solutions to solving those problems. But there's a huge amount of research effort being focused at that particular area, machine learning now, because this is obviously so valuable to industry.
We're assuming that quantum computing is still at a very early stage. It's barely off the ground. Is there a lot of effort being put into it? Is this really seen as the next big thing and everybody better get on board pretty soon?
What most reasoned technologists would say is that optimistically, quantum computing will augment or displace some parts of classical computing. So certainly, quantum computers you could treat as a specialized processor, like a GPU or an FPGA or an ASIC. Something that's going to do some tasks extremely well, but it will always be treated probably as a coprocessor. The other thing I'd like to talk about is what the mission should be for any practically minded commercial enterprise now. If you are in the private sector and you're looking at quantum computing, the really fascinating challenge is to work with, as you say, these primitive early generation processors, these quantum processors, and figure out ways to use algorithms to squeeze as much power as possible out of these early machines that are not error corrected and that do not have a large amount of capacity. This is an absolutely fascinating challenge, and our company, for instance, is seized upon that. In order to try to solve that problem, in order to try to have, in the near term, to try to make these machines, these processors useful for industry, you have to start from hard industry problems. You have to look to computing bottlenecks that exist in industry today, and you have to look at the mathematical structure of those problems and take a view. There's a rational mathematical approach to doing this, to look at which of these problems are amenable to being run on quantum processors, and those are the things that we focus on. So go ahead.
Now, is quantum programming, does it require a whole different language from conventional programming languages? Do you really have to think in a different way to utilize the capabilities of quantum computers?
You do. These are machines that are not deterministic. In other words, you're not getting a single answer, but the solution that's returned by a quantum computer represents an answer, a solution that has a high probability of being correct.
So
now,
probabilistic calculations with lots of variables?
Yes, that is correct. In fact, what's happening is that the hardware vendors, so the groups that are making hardware, and software groups like ours, are working very hard to abstract away all of that programming and processing complexity. The real goal of any, again, self-respecting commercial enterprise in this space would be to sufficiently abstract this complexity away so that classically trained devs and quants and programmers and data scientists who have no presumed background in quantum computing can access these processors without any specialized training. So what you really want to do for the mass market, these are enterprise users, you want to have these enterprise users being able to stay in their high-level languages like Python, Java, C++, and allow them to simply access function calls and to target these quantum processors while kind of sitting at their laptop and not worrying about energy barriers and gate schemes.
I think we have one more image. Could we see that last image, please? Okay, so what are we looking at right here?
Well, you're looking at a processing unit embedded on a circuit board, and I suppose really what this image is supposed to suggest or lead to is what would be considered kind of the holy grail of quantum computing. As you remarked, there's a lot of physical infrastructure attached to these early generation machines. If you look way out into the future, what you would want is to have a quantum processor, a quantum computer, kind of operate at room temperature without special environmental protection and just being operated every day. There's a long way between where we are today and where that happens. An interesting point is, though, that really doesn't represent an impediment to integrating quantum processing into classical compute workflows. The general assumption, and it's not a huge barrier, is that quantum computers will attach to the cloud. And we use cloud computing kind of, it's pretty ubiquitous now. So this is just another processor that's in the cloud, and it will solve one part of a larger problem.
Now, you're CEO of a company called QCware. What does QCware do with quantum computing? What niche do you occupy?
Right. Our real job, if you looked at our company, we are a team of quantum algorithm researchers. And what we're trying to do is bridge the gap between these real-world enterprise problems and quantum computing hardware. And so, to an extent, we start with quantum algorithm primitives that have already been invented and extend those algorithms so that we're connecting to these real problems. And in other cases, we're actually inventing specialized algorithms to solve problems. So we are a business, I believe very, very strongly that a really functional company is one that has a superior team, a superior product, and customers. And we've decided very early that we weren't just going to be a Silicon Valley company that raises VC money and burns dollar bills for a few years to figure things out, but we want to test all of our hypotheses with customers. And so we're very fortunate to have in our investor base and customer base groups, at least that are publicly announced, including Airbus, Goldman Sachs, Citigroup. I'm not sure which other large corporates I can announce, but if you look at the Fortune 100 industrial companies, at least let's say the industrials within the Fortune 200, we have a very nice small fraction of those companies that we are currently working for. And when we work for these companies, our mission is to take a hard problem and to figure out how to map that problem onto a quantum algorithm and run experiments on these early generation quantum computers, and to work with a company to show ways to achieve what is called quantum speed up for their problems on these machines.
Now, do you have your own quantum computers, or maybe they're not available commercially? Maybe a few big companies like IBM have them and you access them through the cloud. Company
Yes.
gives you a problem and you use your algorithms, do cloud processing and return a result?
Yes, something like that. So the hardware developers have been extremely invaluable partners to us, and they're extremely supportive of developing a quantum software ecosystem. And what that means to us is we have partnerships agreements with these hardware vendors. So when customers have problems that they want run, those problems are going through our software stack, which is deployed as a cloud service. And we're running those problems on these quantum computing hardware platforms.
Now, do a lot of companies feel that this is something they have to get in on, even though it's not quite clear, like in the early days of the internet? We don't know what we're going to use it for, but this is new territory. We better stake out a position somewhere. Is that something similar to
I think
quantum
that's
computing?
a very good characterization. So we spend all of our time working with enterprises. That's what we do. I think it's fair to say that every large industrial company globally that has a healthy R&D component and that uses high-performance computing resources today has quantum computing at the very least on its strategic roadmap and is taking small calculated bets. They're not betting the farm, but they're making small investments to start to understand this technology and what it means for their company, what the opportunities are and what the risks are around not, for instance, trying to understand what it could do for their business or their competitors' businesses.
Now, how is quantum computing going to affect the life of the average person? If an average person says, what is quantum computing going to do for me at some point in the future? What can you tell them?
I think it's hard to look too far out in the future, but I think the initial impact will be indirect. It could result, for instance, in better optimization of scheduling for transport and logistics, which could have an effect on the economic cost of tickets or moving people or freight around. It could have an impact on reducing risk in a financial system if you can more efficiently hedge financial transactions. It could, if on the artificial intelligence and machine learning side, it could mean that you have more responsive digital assistants, that there's better interaction, better man-machine interaction. Those things are something that an individual like you and I would observe, but more indirectly. I think that the first major impact will be inside of large enterprises that are working to solve hard problems. They're working to resolve bottlenecks in their compute workflows, which of course result in economic benefit, but that's really where they will directly see gains. They'll see what they want to achieve, which is shorter time to solutions for hard problems to give them an edge.
Is there any government-funded research right now? Has the government determined that this is a matter of strategic importance that it has to promote?
That's a great question. The U.S. government has recently passed some legislation. It's called the National Quantum Initiative, and it has allocated or enacted a law which is requiring certain government agencies to allocate, the number is $1.2 billion over a small number of years to support research and development for quantum technologies broadly. That's quantum sensing, quantum communications, quantum computing, quantum metrology. But the U.S. government is doing this, and the U.S. government is paying close attention to what is happening in Europe at a supranational level for having funding of this sort, and also in China for what the Chinese government is doing in a very centralized and deliberate way to try to advance quantum technology. So the U.S., it's very, very important to the U.S. to preserve national competitiveness in quantum technologies.
You know, I have a lot more questions, but unfortunately I'm not going to be able to ask them tonight because we are out of time. I'd like to thank my guest, Matt Johnson, CEO of QCware, a quantum computing company. Thank you for watching. Visit our website, www.futuretalk.net. For Future Talk, I'm Marty Wasserman, and we'll see you next time.